Hello everyone. Today I'm going to try and show you how to build one of these, an Agon Light, my newest microcomputer. And I will assume that you will start from one of these. This is a partly populated PCB made and populated by PCBWay. I just asked them to populate the tiny components because it would take forever to do those by hand, and also the two QFN chips that you see there, which are very hard to solder by hand. They also populated the two electrolytic capacitors. That was my mistake. I left them in the BOM. You don't want them to populate those because it breaks. It creates an irregularity on the back of the board, makes it more difficult to align the SMD chips. Now, it's very important if you're going to solder this stuff by hand to ground yourself with a wrist strap and to ground the mat upon which you're going to do the soldering. Remember, these are CMOS LVT chips. They are very static sensitive, so don't skip on this. Now, PCBWay put solder paste on all the pads, including the pads that they were not supposed to populate themselves. I understand why they did that. Many hobbyists ask them to do that because they think it makes it easier to solder by hand SMD components. That's a fallacy. It's very difficult to align a chip on top of these bumps. The pins we want to go in between the bumps, not on top of them. So this is not the way to go. PCBWay already promised me that next time they will not apply solder paste to unpopulated pads. And what I did, and what I would suggest you to do if you get these pre-tinned pads, is that you remove that solder. And to do that, you need bevel solder tip, like this one. This is 2.5 millimeters wide. It's appropriate for this specific board. You want a large one because you want good heat transfer through the solder wick. So you need a large bevel to do that. And beyond that, if you use good solder wick with flux already in it, it's just a matter of very gently rubbing the solder wick along the long dimension of the pads so you don't rip them. Remember, these are not through-hole pads. They are not anchored through the hole, the plated hole to the other side. So they can very easily deglue. So do it gently, but do remove the solder paste so it will be at all possible for you to align this fine pitch QFP packaged chips on there afterwards. Now, after you've removed the solder paste, you have to clean it. I recommend you use Kim wipes. They are static safe, ESD safe. And you can use that little pad, lint-free pad, to help you gently rub the wipe with IPA on the pads to remove the flux and the residues. Now, the way to go about it is to first apply a layer of liquid no-clean flux. And that has two purposes: to make sure that the solder joint grabs under the pin as well, and to create some stickiness that allows you to align the chip more easily. Before we start, this is just a reference picture. The red dots show pin 1 of each chip. The chips have a little circle to show pin 1. I'm also showing the positive terminals of the buzzer, the electrolytic capacitors, and the LED, just as a reference. Now, as I was saying, after you've applied the no-clean flux using a flux pen, you can position the chip on top of it using that little tool with a suction cup. If you press the button, you create suction, so you can drag the chip and drop it on top of the pad, almost pre-aligned. But then you need to do some further alignment, and that flux that you pre-applied there will create just enough stickiness to allow you to perform that alignment without the thing dancing all over the place. So I would drop it on top of the pad, as close to the proper alignment as I can, and then I just press the button and it will release it. There we go. And then I just put it under the microscope, and that's what you see with partial magnification. I'm using more or less around the middle of the magnification range, so I can see several pads, but still with enough detail. And then using some tweezers, these are tiny tweezers, you can just sort of caress the chip into place. And you see the chip doesn't move too easily because of the stickiness of the flux, which has these two rolls. to allow alignment and also to make sure that when you apply solder that the solder joint forms under the chip's pins as well. So you just sort of caress the chip into position. Now I'm not editing this. This took I think about 7 minutes to do, and I will make a mistake halfway through this, so I basically have to start over. But I thought if I were to edit this, I would give you a sanitized picture that doesn't reflect reality. You would think that this is very easy, very straightforward, and you'd get frustrated if you try to do this yourself. So I'm showing you my reality. I have done this many times, and I still screw it up. So this is unedited. I'm caressing the chip into place. Sometimes the flux sticks too much, so I have to give it a little bump, and that bump may go wrong and may misalign the whole thing, and then you basically have to start over. But the key message here is be patient. Just keep on caressing the chip into position, checking all 4 sides, because if you adjust one, you may misadjust another, like on top, as you see now. I adjusted everything else and the top went out of alignment. So you gotta be patient. You can give it a little nudge on the side if the caressing doesn't work. There is always a risk if you do that it will go too far. That's what you see me do right now. Just a little gentle, very gentle nudge with my tweezers. So this is in real time, and this is what I went through. I am a little bit of a perfectionist. I think a lot of people would have stopped by now, because the pins are more or less in position. They may not be completely centered, but they are more or less in position. This would already work. But I like them to be centered. I want them to bullseye the middle of the pad and to be symmetric as well. You see me gently caressing that pad into position. That's me. You don't need to be like me. You probably could have stopped by now. This is already good enough. And I think I'll screw it up around any time now, because as I'm trying to caress it into position, and then I decide to nudge it a little bit, and I think it goes too far at some point. Yeah. yeah, now I can't caress it back. It went too far. The flux is already beginning to dry, so it's sticking a little more. So this is it. I'll just let you enjoy the rest of this drama until I finally sort of get to a point where I can leave it and I'm convinced myself that it's good enough. Notice that there is absolutely no way you could do what I'm doing now if there was solder paste already on the pads, all those bumps on the pads. The pins would just fall in between the bumps, and there is nothing you would be able to do to adjust those. So this little story that goes around the hobbyist community, that it helps you to pre-tin the pads for SMD soldering, maybe that works for an electrolytic capacitor or a very large size resistor. But for everything else, it's not the way to go, guys. The PCBs already come with the pads tinned, a very flat, thin layer of tin. That's it. You don't want anything else, otherwise you can't align anything. You just apply liquid flux to the pads before you put the chip on top. So when you apply the heat, the solder will flow a little bit underneath the pin as well. That's the way to go. Not any pre-tinning. You will make your life absolutely impossible if you try to solder a QFP chip, let alone a fine pitch QFP like this chip. It's completely impossible. Now notice that I'm still caressing the thing. You may think that the chip is not moving as I caress it, and it's hardly visible after each stroke, the movement that the chip makes, but it does move. If you just stroke it several times, you will notice under the microscope that it does move a little bit. Now, at some point I need to increase the magnification. There it is. because I want one to be able to do very fine tuning at the end of the alignment. And I also want to do an inspection before I tack two corners of the chip. So I'm going for a little bit more magnification now. You have to play around with the proximity of the lens and the focus as well to get the right magnification. And at this point, I think I am already in inspection mode. I'm just trying to convince myself that everything is in place. A little more caress for final fine-tuning. It does move a tiny little bit with each stroke. It does help. It's a matter of having enough patience to make it. You see, it does move. Having enough patience to make it as close to perfect as you can do. For me, the reason I do these things, I design these computers and I build them, is for pleasure. So I want it to be very near to perfect because that's what makes me happier. Notice that there was some solder mask partly missing between two of the pins. After I solder it, you will realize that that solder mask is missing. I think it was removed when I was removing the solder paste applied by the manufacturers when I was trying to wick that away. Solder wick is not something that is suitable for SMD rework, SMD work. So I think the solder wick just removed a little bit of the solder mask. But it was not a problem. I could solder it, as you're about to see, without creating any short circuit, even though there was a piece of solder mask missing because of wicking away the solder paste. Now, this is time to change the tip of the soldering iron. I will still use a bevel tip, but not a 2.5 millimeter one. I would use a 1 millimeter bevel tip because that's the size that is suitable to drag solder a fine pitch QFP package as we are about to do. You can hardly see the tip. It is a bevel, although it's hard to see. Under the microscope you will see that it is a bevel. Then you pre-tin it just a little bit of 60-40 solder. You don't want lead-free solder for this. And then you just press it and it looks horrible. There are short circuits there. It doesn't matter. This is just to tack it in place. I tack 4 pins on one side and then 4 pins on a diametrically opposed corner of the chip. And you see how big the bevel tip looks under magnification. This is just 1 millimeter across. So it looks ugly, looks terrible. It's no problem at all. Two corners are tacked. So now I'm going to solder the two sides that are not tacked, and I apply no clean solder paste before. I pre-tin the tip, and then I just gently go over each pin, dragging the solder blob together with the soldering iron's tip. If you pay attention, you see that the solder blob goes along with the tip because I used enough flux paste. And the secret is to use enough flux paste to do this, to press it down enough to make thermal contact, but not so much that you bend the pins. And that's where the experience comes in. How far, how strongly do you press, and how fast do you move? And then while the flux is still there to reduce the glare and the diffraction, we can inspect the result. So now I'm going to the other side that is also not tacked, applying the flux paste, and with the pre-tinned 1 millimeter bevel tip, I go over that other side, dragging the 60-40 solder blob with the tip, while I press down gently on the lower part of the pins. Not on the top part, just the lower part of the pins. And I'm looking down the microscope as I do this to watch the wetting action. Now the final 2 pins often get shorted, as you see there. If that happens, forget solder wick. Solder wick is not appropriate for SMD rework. You just clean the tip in iron wool, and you just apply it there again, and you pull it out. That's it. No solder wick. You will get these shorts regularly, And this is the way to remove them. Just clean the tip and pull out the blob. And then we inspect with the melted solder, the melted flux paste to reduce the glare. We inspect that everything is soldered and there are no short circuits. Now I did 2 sides and now I'm going to clean. If you want to do it very well, you clean after every side. You solder one side and you clean, solder another and you clean. And the reason is you don't want the flux to harden under the chip. And it hardens in minutes. And then it becomes very difficult to remove. It will sort of suck humidity from the air, suck dust, promote corrosion. You don't want that. So you want to clean it after you solder every side. So do what I'm saying, not what I'm doing. I'm doing 2 sides at a time. And you use Kim wipes, IPA, and that little pad, soft pad, to just have the wipes absorb the flux. Now, once everything is clean, we apply flux paste to the 2 tacked sides that already have some solder in a couple of the pins. Usually this flux paste comes in a syringe. Once you've applied it, we have to pre-tin again the tip, the bevel tip, 1 millimeter wide bevel tip of the soldering iron. Now I put even less solder now, very, very little, because the tacked pins already have solder in them, and that solder will flow together with the tip. So you need even less pre-tinning of the tip now. So there we go. Those were the pins that were already tacked. The solder that was in them comes along with the tip of the soldering iron now. You can observe the wetting action as the tip goes down the row of pins. And you want to observe it because that's what allows you to calibrate how fast or how slow you should go. You don't want to dwell on any one pin for too long, for more than 3 seconds, because that could damage the chip. So now we inspect again, looking through the melted flux paste, which reduces diffraction, reduces glare, allows us to see well. And then we clean that. Now I'm doing it the right way. You solder one side, you clean it. Before you solder the other side, you don't give the flux a chance to harden underneath the pins or underneath the chip where it can never go away anymore. Same procedure, Kim wipes, IPA, and then you just press it gently down with a little soft pad so the wipes absorb the flux and remove the flux from the board as opposed to just spreading it around. Now that's the other side that's been tacked. You can see the tacked pins looking very ugly and shorted. So we apply the flux starting from there and down the entire row, which you can't see here because it's out of the field of view. And then with a pre-tinned tip, starting from the tacked pins, we again just go down the row. I'm not editing this stuff out, only the really unnecessary parts, because I want you to have an idea of the different conditions that you come across when you're doing this, and also have an idea of how long it takes to do this. So you don't come away with a sanitized view thinking, oh, this is easy and fast and straightforward. It is straightforward, but it is delicate and it can be time consuming. So no bridges left, no short circuits, everything looks good. So we can do a final clean of the CPU. I just soldered in the CPU, which has the finest pitch. So now we just do a final clean using the good old method that I already shared. Now this is another pass under the microscope. This is a final inspection. I'm using that lint-free soft pad and with a lot of IPA in it to clean it along as I move the pins under the microscope. And I inspect everything very carefully now without flux, only with IPA that is evaporating as I look down the scope. So I go down, cleaning it very gently with the soft pad with IPA embedded in it, and just checking not only the lower part of the pins that contact the pad, but the upper part as well, because you can have short circuits, solder short circuits on the top part as well. Some little blobs of solder that was left behind. So you want to look at everything, and you want to make sure that the solder joints are consistent. In other words, that they look like one another. That's what the IPC requires, that they are consistent. You want to make sure that they have enough solder to make a proper joint, but not excessive solder. You want their surface to be round and smooth and reflective, because if they look crackly and dull, that's a sign of a dry solder joint that may not be a good joint at all. So that's what you're looking for: shininess, softness, consistency, lack of short circuits or bridges, and you also don't want to have a pad that has so little solder that the connection may not be reliable. So it's important that you do this after the solder job is complete, so you can focus purely on checking if everything's up to standard. This is the time to check for problems. If you miss a short circuit here or an unsoldered pad at this point, this will throw you on a wild goose chase after you turn the computer on, because the last thing you will think about is a problem here. Now you can see there the missing solder mask between pins 4 and 5 from the top. I think I damaged that when I was removing the solder paste that was left there by the manufacturers, which is a sign that you have to be very careful when you use solder wick on surface mount pads. Through-hole pads, they are little cylinders. They are anchored in place by the through-hole plating and the pad on the other side of the board, so they are mechanically very stable. These SMD pads, they are just glued on the top of the board. They are not anchored through-hole or on the other side. They are very fragile. So solder wick and SMD rework is not a good combination. The fact that I had to do that, to remove the solder paste, was a little extra risk, but as you could see before, even though the solder mask was missing, there was no bridge, there was no short circuit. And after the soldering, if there are no short circuits, then it doesn't matter whether the solder mask is there or not. It will have or not done its job already. It's no longer needed. Okay, the CPU is complete. Now it's time to install the SRAM chip. Same procedure, no clean Flux pen. I already cleaned the pads with IPA, and I'm spreading a more or less generous layer of this liquid no clean Flux for the stickiness and to make sure that when I apply the solder joint forms also underneath the chip's pins. Using that the same little suction tool, I pick up one of the SRAM chips, and as you see, the tool is not very reliable now. It makes me drop the chip a couple of times. And I already tried to drop it in more or less aligned by eye, so the work under the microscope is easier. There we go. And then I put it under the microscope. And it's almost in place. It's not symmetric. The bottom and top are not symmetric. So the bottom sticks out further into the pads than the top. So I try to move it up a little bit. I try to caress it upwards, but that doesn't do much because the liquid flux is a little too sticky. Once you have the chip aligned, and this is a tip, once the chip is aligned, what you can do is with your tweezers, you press down on it from the top to make it adhere to the flux. Increases the stickiness if you press it down a little. But do that only after it's aligned, otherwise it will make your alignment work more difficult. Now, as you can see there, side to side it's well aligned, but there's a lot more free pads on the top side of the chip than below. I'm trying to caress it upwards, but it's not moving enough, so I think I will need to nudge it. You could already solder it as it is now. Electrically, it's fine, but I don't like the asymmetry. And you see now the thing danced on top of the flux, like skating. It skated on the flux and went out of alignment. So now I have to gently nudge it sideways. I nudge it a little too much. So I try to caress it back. If not, I will nudge from the pin itself, nudge it back. So now I think it's more or less okay. I press it down on that side. I think I'm satisfied now with the current alignment. So I pressed it down. I probably press it down on the top as well to make it stick. Or I'm just inspecting. Now you have to inspect everything. Once you've stopped touching the chip, you have to inspect the whole thing. Because if you caressed it on one side and the alignment improved in the field of view of the microscope, you could have destroyed the alignment on some other place on the chip that is outside view. So once you are more or less satisfied with it, you have to check everything, every single pin before you say, okay, this is now properly aligned. As you see, I screwed it up again. I nudged it too hard. I'm not editing any of this out. I don't want to give you a sanitized view of what it takes to do this. And the tweezers shake a lot. It looks like I have Parkinson's disease. Because these are very, very tiny tweezer tips. The magnification makes, you know, every movement looks enormous. So it looks like I have Parkinson's. I do not have steady hands. You probably already noticed that even if you take the magnification into account, I don't have really steady hands. So that should be an encouragement for you. If with my hands I can do this, then you certainly can do this too. There. I think now, no, it's still sideways, not well, so I will caress it. You keep this word in mind, it's a caress. That's what you want to do. Anything more than a caress may destroy your alignment. So I'm just caressing it with the tweezers. I'm not even pressing the tweezers down too much. You may notice I'm not scratching the epoxy at all. So it's really just a feather-light caress. Yeah, now it's aligned. So now I'm pressing it down. You see what you see me do now? I'm pressing down on the chip so it sticks to the flux. And that will improve the stability when I drag the soldering iron, or not drag, when I put the soldering iron there to tack the corners. And again, I inspect everything and I press it down for adherence. This is all in real time, so the time you're watching me work on the alignment of this chip is the time it took to align this chip. Yeah, it looks stable and well aligned now. Few more caresses. I don't know why I'm so perfectionist with this one part. I think sideways I'm not too happy. I think it can be better still. It probably can, but this is perfectly good enough. And then I do one final pass on everything, because every time you touch it, you could have misaligned something out of view. So you want to do a final round of everything. Look at every single pin, every single pad, after you've touched it for the last time. Okay, now it's good. So I pre-tin the soldering iron's tip. I hold the chip down with my tweezers. You don't see it, it's out of view, but I'm holding it down with my tweezers. And I tack 4 pins on each side. I did it on the other side as well. And now I will apply the flux paste. Now remember that there are only 2 sides now, not 4. So both sides are tacked. So what I would do, not to compromise the stability, I would not drag solder starting from the tacked pins. I will do the drag soldering 5 pins down the row, so I don't reflow the pins that are tacked, because if I reflow them, I will lose their strength and I may lose my alignment. So I'm starting down under. You see some 5 or 6 pins down under. So the ones that were tacked, they are up there, up the screen. and they are still holding the chip in position, in alignment. And this is like you've seen before. The pitch here is a little bigger than the other chip, the CPU, but still very fine. Remember, the soldering iron's tip, which looks gigantic on the screen, that's 1 millimeter side to side, only 1 millimeter. There we go. And then while the flux is still melted, I will go back and reflow the tacked pins so they look good. There we go. There we go. All the bridges are removed and the solder joints are now appropriate. Again, you don't press the soldering iron down too hard, but you also don't go too feather on it, because otherwise you don't make contact and you don't transfer heat. Now I'm inspecting it through the melted flux, because it helps reduce the glare and the diffractions. And then I find a pin that seems to have too little solder, so I go back with a pre-tinned tip and I reflow that one, so now it has more solder, now it looks good. And the final two pins also don't have enough solder, clearly. So I go back there with a pre-tinned tip and I reflow them, and yeah, now it looks okay. So that's another reason to do this inspection with the solder, with the flux still melted on top. It allows you to rework things before you clean the flux. So I already cleaned the flux at this point. I'm doing the final inspection with that little lint-free ESD safe pad with IPA in it. And I'm making sure that everything looks good even when the flux is not there. And it's a final round of cleaning as well. And it's important to do it with a lint-free soft pad, because if you do it with, I don't know, with a cotton bud, you will leave lint behind, pieces of cotton that would tend to absorb humidity and stick to dust and will promote corrosion. So one side is checked, so I flip the board around to inspect the other side. Everything's already pre-cleaned with Kim wipes, IPA, and all that stuff. This is just a final inspection and cleaning round. Notice that there is a little blob of solder on that decoupling capacitor to the right. I don't like the way that looks, so I'll rework that quickly. I just don't like that thing sticking out to the side. It could eventually lead to a short circuit. It's too close to the pin, so I just touch it a little bit. Yeah, okay, it's sorted. And go back to cleaning it with IPA on that lint-free soft pad. This should be good enough now. So we just go down the rest of the row, inspecting everything. Final clean. Now be obsessive about making sure that there are no errors, no defects left here. It will save you a lot of time and headache later. The time to check is now, not when you turn on the computer. Alright, second chip is done. Now there is one more SMD chip. That's the pseudo SRAM, the PSRAM. It's an 8 megabytes part that talks to the video and audio coprocessor next to it, which is the ESP32. This is SMD, but it's not fine pitch, so it's much easier. I'm doing the same thing. I put it in place, press it down on the flux that was already there, so it sticks. And then I would do the fine-tuning alignment under the microscope. Now at this point, the flux was already pretty dry. I had applied it a while before, so it loses some of its properties of adherence. And as a result, you see that the chip is dancing all over the place. Even if I feather touch it, it already goes out of position. So I should have reapplied the no clean liquid flux with the flux pen just before trying to align this chip. Now it's okay, but I try to make it even more perfect, and you will see I'll screw it up because the flux is not sticking enough anymore. I'm trying to caress it, but the pad is a little rough, so I try to nudge it, and I will lose the alignment. You will see. No, it's already back. Now it's okay. Now it's okay. So I press it down to try to make it adhere to the flux. Now you see me pre-tin the tip of the soldering iron, but I forgot to press record when I was actually soldering this. So I don't have footage of the actual soldering process. I will show you footage of the final inspection, but it's trivial. In this case, you don't drag the soldering iron because the pins are too far apart. So you just press down on each one of them, one at a time, with a lot of flux paste on top and a pre-tinned tip of your soldering iron. And you pre-tin again after a couple of pins if you don't have enough solder left. So this is the final inspection. This is the easiest of the chips to solder. Too bad I lost the footage, but yeah, there's not much lost here because it's the easiest of them all. This is just the final inspection to make sure that all the joints are okay, because I don't want to be thrown into a wild goose chase when I turn this computer on, just because one of the solder joints is actually not made, there isn't enough solder, the contact is not made, even though visually it looks like it is, and God knows when I will find that kind of problem. That's extra IPA in there. I think I saw some residual flux. Yeah, there is still some residual flux. Now there is a little bit of solder there. I'm wondering whether that one is loose. I don't want it to be there if it's loose, because it could go down the chip next to it, that QFN chip, and cause a short circuit. But it's adhered, so that's okay. That was just a little bit of the solder mask that peeled off and solder stuck to it. That is not a problem. So yeah, this completes the SMD soldering part, which is the part I wanted to illustrate to you, because not many hobbyists are used to doing this. I will also show you two of the through-hole parts, and I will understand why, because there are some specific Agon things about these two parts. The regulator has VCC on the tab or on the chassis, and the large pad with those thermal vias on the board should contact the back of the regulator electrically. So you want to clean that large pad, and you want to clean the tab of the regulator, or the back, or the chassis of the regulator, so they make good electric contact, and you don't want to apply thermal paste to that tab, to that pad. I'm just cleaning it with IPA. Don't put anything there, no thermal paste, no nothing, because you want there to be electric contact. This will increase the surface area in which VCC goes into the power planes of the board. Now these pins, the leads have a thick part and a thin part. The board was designed for you to bend the leads down 90 degrees just after the thick part. So that's how you begin. You just bend it down 90 degrees, a tiny little bit after the thick part, and that should allow you to have good pre-alignment of the regulator's hole with the hole on the board, because the regulator needs to be screwed or bolted on the board. So insert it, and now I will push it up or down a little bit, just to fine-tune the alignment so the two holes match one another. You can put a screw through both of them. But if you bend the leads in that position, the pre-alignment will be good enough. You see, just with my fingers I could just adjust it to get a perfect match. And now we need a nut, a bolt, and a few washers. These are 2mm bolts. The hole is 2.5 millimeters wide. The hole on the board is. So use 2mm bolts and nuts and washers. That's one metal washer. And we also need one non-conductive washer. I'm using a nylon washer. And the reason for that is that on the back of the board there is a ground flood, copper flood, while that screw, the metal screw, will be VCC. So if you use a metal washer on the back of the board, you will have only the solder mask to prevent a short circuit. So you don't want that, so we will isolate the bottom of the board with a non-conductive washer, like a nylon washer. I'm also suggesting that you use a lock washer that you saw me take last. So I first put the normal metal washer on the boat. I want it to have the right side up. So there goes the washer. And then below the normal washer, you put the lock washer to make sure that the pressure and the tension remains over the years. And then you put the bolt down the two holes. All of this is before you solder the leads. You don't want the solder joints to take any mechanical stress whatsoever. So you deal with the mechanical part first. There we have it. The nut, the normal washer, and the lock washer. And then on the other side, we put the nylon washer. So the nut doesn't touch the board because there is a ground flood on the bottom of the board, while that nut will be contacting VCC. So you don't want to trust the solder mask there. And then you just maybe use a pair of pliers just to hold the nut underneath, and you tighten the bolt through the lock washer, and then it will remain in place. And there you have it. Everything is bolted together. There is no solder still. And the way it would look like is more or less like this. You see the two washers below the nut. You see the large exposed metal pad. And that's the little nut and the nylon washer on the other side. Now what you do now is you press down on the leads to make sure that the regulator is totally flush against the board to maximize the electric and thermal contact between the tab of the regulator and the metal on the board itself. So after you ensured that, then you just bend the leads, and now even without thermal glue, the regulator is solidly pressed against the board. And that's good for thermal reasons and for electric reasons as well. You want to have a large area of conductivity between the VCC pin or the 3.3 volt pin of the regulator and the board. So now I applied some flux paste. I am using a conical solder tip now, 1 millimeter, but now it's conical, not a bevel. Bevel doesn't work for this. You want a general purpose conical tip. Again, I'm using 6040 solder, leaded, and then I just solder the three leads of the regulator. They are now taking absolutely no mechanical stress because you already bolted it in place, you already twisted the leads, so it's already settled in place by the time you are soldering them. And then after the three of them are soldered, we just clip the excess leads and give it a clean with that tried and trusted method using Kim wipes, IPA. Yeah, I'm just clipping the excess leads now. This is all in real time. Again, I don't want to give you a sanitized impression of what it takes to do this. There's still one lead that's a little too big, so I go back and clip it off a little further. I don't think I will show you cleaning this, or maybe I will, because it's important to show you that you should clean the flux after every part, or even after every side of a chip, not to give the flux paste a chance to dry and become encrusted. There we go. So Kimtech Science, these are the wipes I use. They're called precision wipes for whatever reason. It's not about precision in this case. They are ESD safe. And then you just put the wipe on top. And then you use this the ESD safe little brush. I'll show you how it goes. So you put the Kim white on top. You spray the IPA. And then you gently poke down on the Kim wipe, so the leads puncture the key wipe, and the wipe sort of touches all the pads fully from all sides. And it will absorb the flux. Then you move it around a little bit more, poke it in place again, so there is good contact. Give it a little wipe, and all the flux will be transferred to the Kim wipe and not be just spread around the board. And all this stuff is ESD safe, so there is no problem rubbing it around and, you know, like I'm doing. You're not going to create static. The brush I'm using is ESD safe, so nothing's going to blow and get damaged because of this. And you see there, it's completely clean. There is no flux residue left. And on the top, some of the solder flowed down the hole and made contact with the pad on the other side as well. That's okay for large leads like this. When you're soldering, you know, small chips, you don't want much solder to flow, but in this case I wanted it to be like that. So these are the two main components that I wanted to show you, the regulator and now this buzzer. It has a little plus sign on top, and you want that plus sign to point upwards on the board, to be close to the PS2 connector that goes on top. You see, the plus goes up. If you're reading the silkscreen of on the board, the plus sign goes to the top. It's the upper side. That's how you should solder this. The silkscreen does not have a marking for this. It has very little markings on the silkscreen because it is such a tiny board that it makes no sense trying to write too much on the silkscreen. Now I'm going to use blue tack to affix it in place while I solder it. I'm not going to show you the soldering of the other through-hole components, the connectors, for two reasons. One, I don't want to patronize you, pretending to teach you to do something you already know. And two, if you don't know, and if you do need instruction about how to solder through-hole components, then you should not attempt to build an Agon yourself. An Agon is not a project for beginners. That's not how you learn electronics. So I don't want to encourage you to try your hand with an Agon if you don't feel comfortable already with at least through-hole soldering. So what you see me show you now is the solder paste. The blue tack is making sure that the buzzer is in position. So now we just flip it around, turn on the solder fumes extractor because I'm using leaded solder. I don't want to breathe that in. I want to leave long. And I solder it in place. I have not only the solder fumes extractor on, I also have a ventilator pointing to a window and pushing the air out of the room. So there it is. I'm not going to show you the cleaning again, or will I? Maybe I will, because it is important. I don't know. Let's see what's going to appear now. Yes, I do show you the cleaning. You should clean the flux after every component if you haven't gotten that yet. You don't want this stuff to dry up. There we go. A little more cleaning. That's it. No flux residue left. It's shiny and mirror-like. If you have an ultrasonic bath, then you know your stuff. You don't need to do what I'm doing now. You know how to do it better. But in that case, don't put this buzzer before the bath. Do the bath and apply and solder the buzzer at the end, because you don't want water to get into that cavity. It may damage the membrane of the buzzer. And if you have an ultrasonic bath, you're probably not watching this video anyway, because you know your stuff. If you do everything right, this is what you should get at the end. And that's how the board should look like on the back side. It's visibly hand soldered. But there are no dry solder joints. Everything is shiny. All the flux is clean. And I've cleaned the flux without an ultrasonic bath. So it is possible if you use IPA, Kim wipes, and ESD safe brushes. And at the end, that's what you get. It's very gratifying. I didn't design Agon to be pretty. All the entire layout, all the routing has technical reasons to be the way it is. But I'm happy that I think it does look good, doesn't it? It is a cute board. So it's very gratifying to look at it at the end and know that you've built it. And I hope you get that pleasure as well. If you're doing this for yourself, that you feel gratified with the product of your work at the end. It's a cute board, works beautifully as well. And if you are soldering this stuff commercially, I hope this video has helped you with the more difficult parts, like fine pitch SMD soldering. There is a reason to do this by hand and not ask the PCB manufacturers to do it, because they charge a premium to buy the components for you. And you also have import duties, components from the US go to China, and then from China they come to Europe. To avoid all that, you can solder the more expensive component yourself. And that's what I tried to show. Now, the very final step before you turn it on is check for short circuits between adjacent pads, especially of the GPIO connector, which has a lot of soldering involved, the VGA connector, the ZDI. I always do this offline. I check for short circuits between adjacent pads. You should have the schematics with you because sometimes there is a short, but it belongs there. And then you check for short circuits across the pins of the regulator. Ground is on the right. In the middle is 3.3 volts. It will beep initially while the capacitors are charging, but then you should get above 600 ohms resistance, as you see there, above 600 ohms. And then also between ground and 5 volts, and between 5 volts and 3.3 volts. And if everything is normal, now it's safe to turn the thing on. So this is it. I hope this has been both useful and enjoyable to you. Take care, and I'll see you next time.